Good. I saw that I got actually 2 time slots, so we have time to stop and ask questions. I sat in on some of that discussion at the end of yesterday, listening to all that talk about what to do if you're supposed to be engaging and outgoing and furthering your career, but you're not really comfortable with that. I was thinking, anybody can ask a question. Anybody can come up to somebody after a talk and ask them a question. And people love that. People love it when somebody comes, a grad student or postdoc, comes up after a talk and asks you something. Doesn't matter what it is. So I'm going to talk about the ionospheres of the terrestrial planets. I actually take my title from a paper that was written some 30 years ago by Shunk and Nagy, comparing the ionospheres of Earth, Venus, and Mars. Those are roughly the terrestrial planets, sort of the rocky ones, the Earth-like ones. I'm not going to talk about Mercury because it doesn't have much of an atmosphere. And I'm not going to talk about the gas giants, so-called, or Pluto, because we only have so many hours in the day. So I'm going to try to describe the ionospheres of these planets, how they're produced, and give my take on why it is that they're fundamentally different. So in this first session, I'll give an introduction to the Earth science. Basically, we'll talk about Earth. And I'll give you a very basic introduction to why there are ionospheres and what they do. And in the second part, I will talk about Mars and Venus, their atmospheres, which explains their ionospheres, and discuss a little why Earth is so different, or why Mars and Venus are so different, depending on your point of view. If you're a planet near a star, and there's an atmosphere, then there will always be an ionosphere. And that's because of the presence of ionizing radiation, extreme ultraviolet and soft X-ray and hard X-ray radiation that Harry talked about yesterday. Here's a little artist's conception of this is, interestingly enough, when the artists who built this out of NASA photographs put them around the sun, of course they found an image of an X-ray sun, probably from SOHO, because the X-ray or EUV sun, extreme ultraviolet sun, that looks so much more interesting than the yellow sun that we're familiar with. And so these are the terrestrial planets. Oh, whoops. These are the terrestrial planets. These are the terrestrial planets. Mars, Earth, Venus. And these aren't really in any kind of, well, I guess they're in order if you start here. You start here, they're in order. Yeah. You start here, that must be Mercury, and you go all the way around to this thing, and then this planet-like object. Well, I was saying, you go up to some important person and just ask them a question. Like once I walked up to Alan Stern, who is actually junior to me, but I just to get a rise out of him, I said, so what's the deal with Pluto not being a planet?
That is not the question you asked Alex.
No, it was great. He went off on a rant that was a beautiful 3-minute concise description of exactly why he maintains that Pluto is a planet, which I will not repeat, but you could ask me, and I could reproduce it. It was brilliant. It was an elevator speech on why Pluto is a planet, and but it was fun. It was fun getting a rise out of him. The compromise seems to be dwarf planet. Anyway, so here are the terrestrial planets that have atmospheres as seen from the lunar surface. This part of it is an actual photograph. These parts I just added in. So here are the questions. Here's what I want to think about. People talk about ionospheric layers. You may have heard F layer, E layer, this sort of thing. And why is that? Why are there layers in the ionosphere? So the Earth's ionosphere, we know it's produced mostly, not entirely, by solar extreme ultraviolet and X-ray radiation, but it's still around at night. Why? Now, most of the ionization, I'll show this, happens at around 100 to 200 kilometers altitude above the surface. But most of the ionosphere is up around 300 kilometers. And I'm curious to know why that is. I mean, I hope you are curious to know why that is, and I will describe why that is. And then why are Mars and Venus so different from the Earth? The ionosphere, most people think of the upper atmosphere as being the ionosphere. You hear that all the time, you know. You just heard it. I do ionosphere research. Actually, I'm more of a neutral atmosphere guy. But the ionosphere was discovered first because you could bounce radio waves off of it. Therefore, most people think of that region up around 100 kilometers up to 500 kilometers as the ionosphere. We also call it the thermosphere because it's hot and it's mostly neutral. And then you have this, this historical delineation into layers. The history of this is that the E layer was discovered first. It's the electric layer. They realized that there was an electrified layer up there, so E for electric. And then when they realized that there was also this very extensive ionosphere higher up, I guess it became F, and then they had the D, you know, just to keep things in order. And during the day, it's a little more complicated. People talk about the F1. And during night, the D region goes away. The E region, or layer, mostly goes away. The F layer does not. Here is the thing that creates most of the ionosphere, the solar extreme ultraviolet radiation. Actually, this is the whole solar spectrum out to the near infrared. So you got a full description of this yesterday on this plot. This is simple. I plotted a canonical, empirical solar spectrum from an old model in red at solar max. And then I overplotted a spectrum from the same model at solar min in yellow, because the sun is yellow. And so the variability occurs in this fringe of red behind the yellow. And note that it's a 8 order of magnitude log scale, in log plot actually, and that in the visible and even in the near ultraviolet, the variability is so small that on this plot you can't see it at all. As you get into the far ultraviolet, around 200 nanometers or so, you can just see a little bit of variability. It's on the order of 10% in here. This is the big Lyman alpha line, where you have 50% variability or more. And then as you get into the extreme ultraviolet, it's more like a factor of 2. In the soft X-rays, it can go up to a factor of 10, and in flares, even more. Orders of magnitude increases possible in flares. All of that energy gets dumped into an atmosphere. And this is the big picture view of the atmosphere. You're familiar, I'm sure, with the troposphere, stratosphere, mesosphere, thermosphere. The spheres are separated by pauses. The pauses are local maxima or minima in the temperature profile. And up until you get to somewhere in the stratosphere, there is virtually no change in global average temperature between solar minimum and solar maximum. In the stratosphere and mesosphere, you can just barely start to see some temperature change, which is not visible on this plot. In the thermosphere, the temperature change becomes dramatic, going from a factor of 2 or so, around 600 degrees Kelvin to twice that. And in both cases, you reach this asymptotic value, this so-called exospheric temperature, or T infinity. Now, the reason, of course, that there's this big temperature change in the thermosphere is because that's where the ionosphere is. That's where all that variable solar energy is deposited. I will go back just one. You know, this part of the spectrum is deposited in the troposphere, and it's virtually invariant. And this part of the spectrum is deposited high up, and of course, therefore, you have a lot more temperature change high up. This is the big picture view of the density of the atmosphere. Just the major species, mostly molecular nitrogen, molecular oxygen, low altitude. And I just want to make one important point about this, which is that below about 100 kilometers, the atmosphere is fully mixed due to turbulent processes. And consequently, all these lines, as the atmosphere drops off dramatically, again, 12 orders of magnitude on a log plot, the atmosphere is dropping off exponentially or logarithmically, depending on your point of view. And yet these lines are parallel. The N2 dashed line and the O2 dashed line are parallel because their mixing ratios don't change because everything is fully mixed. About 100 kilometers, all that turbulence stops acting, and we have diffusive separation. Each species starts to follow its own mass, and this lighter stuff floats up high, and the heavier stuff settles out. And the other thing that happens around there is that atomic oxygen becomes a major player. And atomic oxygen being lighter than the others, as it diffusively separates and floats to the top, it becomes the dominant species. And O2 drops off. O2 is getting broken up into atomic oxygen right around here. And so O2 is rapidly dropping and settling out because it's the heaviest. And so most of this thermosphere-ionosphere region is the interplay between the lighter reactive atomic oxygen and the heavier, less reactive molecular nitrogen. Now, I've left ozone out of here. That's going on in the stratosphere and also in the mesosphere. That's, of course, an important part of the so-called odd oxygen picture, but I don't have time to talk about it. So, and of course, many other neutral species. So this is how the solar energy is deposited into the atmosphere. On a plot where basically I put the color bar represents the energy deposition in milliwatts per meter cubed per nanometer. And on this scale, we have the wavelength, just like that solar plot. And here's the altitude showing where in the atmosphere that energy ends up. Here's the stratosphere, absorbing all of that middle ultraviolet stuff. This is creating ozone. This is the ozone layer. In fact, this is the ozone layer protecting us from this radiation, which we would not want to have hitting us. When we get out longer to that, it reaches all the way to the surface. Or rather, here in this region, it's reaching into the troposphere. Out here, it's going all the way into the surface of the Earth and the oceans. As we get to shorter wavelengths, we have absorption by molecular oxygen, creating atomic oxygen all the way up into the thermosphere. And then shortward of that, we now have the ionizing radiation. This is all ionization here. And that, of course, is deposited high up because the cross-sections are large. It's the atmospheric gas cross-sections that determine all of this. Cross-sections for ionization very large, so even though it's a near vacuum up here, you're absorbing solar radiation, ionizing it, and creating the ionosphere. So this is the basic altitude structure of the ionosphere. We have solar min in blue, solar max in red. A lot more of it, of course, at solar max because there's more solar radiation. And this is that F region. The major peak of the ionosphere is up in the F region. And down here, there's a little blip for the E region. And the D region is down here. It's hardly even visible on this plot. It's very weak. During the day, let's just look at the solar max. It's easier to see. During the day, you have a large F region. Then you sort of reach this plateau, sometimes called the F1. And then you have this E region. And during the night, you still have an F region. It's lower in magnitude. It's higher in altitude a little bit. And then, as you go down lower, the ionosphere drops to almost nothing. This is 3 orders of magnitude. There's just a tiny bit of ionosphere here. And this is actually produced by various nighttime sources of ionizing radiation. The geocorona of the Earth, basically photons bouncing around in the extended exosphere of the Earth, starlight, and stray metal ions and little bits of ionization floating around. Now, I am leaving something out here. During the night or day, you can get ionization in this 100, 200 kilometer, the so-called E region from the aurora. And that's very, very important for ionospheric dynamics. But I'm just trying to give you a big picture of how the ionosphere works without going into a lot of the details. So we're just going to mostly talk about solar radiation. I'll give you a little example of how auroral ionization is important at the end. Now, this plot is important because you don't normally see the ions and the neutrals on the same plot. People make a plot of the ionosphere and they show you a plot of the thermosphere, or they plot them on top of each other but on completely different scales. So here they are on the same scale, 10 orders of magnitude this time, just going from 100 kilometers up to, it's called a plasma pause up here. Throughout this region, the so-called ionosphere is mostly neutral. Even here at the peak of the F region, it's less than a part in 1,000 ionized, very weakly ionized plasma. It's not till you get up into the so-called plasmasphere above, say, 1,000 kilometers or so, that the ions start to even compete with the neutrals in terms of their absolute density. Now, of course, they're very important dynamically, electrically, in terms of the magnetic field, but, and chemically, as I'll show in a minute, but they're a very, very small part of the population. And down here in the E region, it's part in a million at best. And the variability is sort of similar. At solar max, the whole atmosphere swells up. It's hotter. The scale heights are larger. I'll define scale height in a sec if you haven't heard of that. The whole atmosphere swells up and is more dense. It's a little counterintuitive. Solar min, it's less dense at any constant altitude. And then the ionization is also commensurately larger at solar max than at solar min. This is just for midday, mid-latitude. This uses typical empirical models that you may have heard of, the so-called MSIS, and IRI is the International Reference Ionosphere. Yeah?
So that is counterintuitive. It's a lower atmosphere that's flowing out.
Yeah, ultimately the source of all that gas is the lower atmosphere. But above 100 kilometers or so, the entire atmosphere is expanding. And in fact, I'm going to, at a fairly high level, but mathematically, I'm going to describe that now and see if that helps the intuition or if it's still counterintuitive. The thing that determines the, yeah. Why the neutrals? Because of the temperature, in essence. There's more to it than that, but the main effect is the atmosphere gets hotter. Here, I'm going to backtrack. Oh, whoops, way to there. Okay, this is the temperature profile we're dealing with. Much hotter at solar maximum, starting at around 100 kilometers. Big gradient in here. And in fact, this gradient is due to all that energy being deposited in this region. That's all the ionization. How does the ionization energy get converted into heat? I'll get to that in a minute. Okay, so here's the very simplified mathematical basis for this. The thing that defines an atmosphere is the fact that its pressure gradient is controlled by gravity. This is simply the pressure equation. The derivative of pressure is the negative of this gravitational force, which is a function of altitude, times the density, rho. Height derivative of pressure equals acceleration of gravity times density. The other thing, of course, that determines the distribution of the atmosphere is the perfect gas law. P equals NKT, or rho over M, where M is the mean molecular mass. I'm imagining we're fully mixed at the moment, so you can talk about a mean molecular mass. Now, I'm going to make a huge simplification. I'm going to take out the variability in G and T. Let's say G is a constant, T is a constant. So now we now have an isothermal atmosphere. Now, dP dZ equals negative pressure times mean molecular mass times gravity divided by Boltzmann's constant times temperature. mg over kT. mg over, that's the inverse of what we call the scale height. So dP dz equals negative P over H. H is kT over mz. It's the scale height. It's the e-folding distance of the atmosphere. It's the height you have to go up in order for the density to drop by 1/8. And this, of course, is now a quite simple differential equation, which we know how to solve because it has simply, it has the variable in the denominator. And whenever we see that, we think, oh, it's something to do with exponents and logs. So this is then the law of atmosphere, is that the change of pressure with altitude is the pressure at some reference altitude, Z, it could be the surface, could be 100 kilometers, Z0, times the change of altitude over the scale height in the exponent. Now, that's for a fully mixed atmosphere. If the atmosphere is diffusively separating, like I showed you the atomic oxygen floating up and the N2 floating down, the projector is overheated. Oh boy.
It's been doing that for the last month. So, you already up until now?
I'll notify the authorities. Yes. Radiation pressure, you mean like solar radiation pressure itself? Only becomes important once you're out of the fluid regime, above 1,000 kilometers or so. Things start to take ballistic orbits. Individual molecules start behaving as if they were little spacecraft. Radiation pressure is an important component of a minor but important component of spacecraft trajectories. But as long as there are enough collisions between the different molecules and atoms, you can describe the gas as a fluid, and that's good to about 500 kilometers, depending, of course, on solar activity, because I'm explaining that the density is very variable with solar activity. Yeah, so all of this applies to a fluid description of the atmosphere. So if the atmosphere is diffusively separating, each of these individual species, I'm calling them J's here, follow their own scale height. They each have an individual scale height, where the scale height of the jth species is kT over m sub j g, where m sub j is the molecular weight of that species. This is that everybody takes their own scale height approach. So if we want to know, get to cover that question of why it is that the atmosphere gets denser when it's hotter. You know, it's not a balloon, right? It's not a concealed balloon. It's an infinite balloon, and when T is higher, H is higher. It takes longer to drop off. It takes more distance upwards to drop off. Hence, backtracking again, hence a curve that looks like this instead of like that. The temperature controls the rate of diffusive separation. The reason that there is diffusive separation is that there are fewer collisions between the molecules and hence less turbulence. In a way, I guess I should say, there's sort of three regimes here. First you have enough collisions so that you're fully mixed and turbulent. Then the major transition you go through first is that you don't have enough collisions to have turbulence anymore, but you still have enough collisions to be a fluid. That happens around 100 kilometers. And then that regime lasts up to about 500 kilometers. And above there, you have so few collisions, you can't even describe it as a fluid anymore. You get ballistic trajectories, and things get yet more complicated. Because there's so little temperature variation down here. Once you get down to 100 kilometers, the temperature variation is very, very small. Right, right. Let's go back one more time. Here's that. Here's this great plot. That. Oh, sorry. Why do the curves sort of converge around 100 kilometers? The reason is because the temperature variation is so small at 100 kilometers. Okay, so let's look. Here, the stuff that's landing at 100 kilometers is, well, just the tail end of this EUV. It's variable. Lyman alpha is another story. It penetrates down into the mesosphere. This is the Lyman alpha line here. And then up in here, all this stuff has very small variability. And then as you get into here, there's it's just 1% or so. So yes, there is temperature variation in this mesopause region around 100 kilometers, but it's small. And so the temperature variation is small. I'm jumping around here. I should do this from the podium because then I can use my magic. Here. See, here's the variability, getting very small, longwards of 100 nanometers, and then almost nothing up here in the middle ultraviolet. And see if I can. Well, I know how to navigate this, but I can't find my cursor, so I'll use this instead. So you get very, very small temperature variation down here. And consequently, very, very small density variation down here. And the density variation is cumulative as you go through scale height after scale height after scale height. If it's hotter, they spread out more and more. And the diffusive separation becomes larger and larger. Okay, so that's the main concept I wanted to get across if you haven't run into it before. And this is a useful concept in solar atmospheres, stellar atmospheres, anything that's controlled by gravity. So now the next question is, how did I make that color plot of showing where all the stuff lands? Well, it's by calculating where the energy is deposited in an atmosphere. It's controlled by the cross sections, how virtually large in a quantum sense the atmospheric gases are. Those cross sections are a function of wavelength. Now I'm going to say, just to keep the display of the math simple, we're going to look at a particular wavelength, one little column on that color plot. I'm going to say at this wavelength, the ionization rate, Q, is the radiation times the cross section times the density. I sub z sigma sub I times n sub z. And from this, we can derive the law of Beer, which is that the intensity of the radiation at any location in altitude or along a path is its intensity when you started at infinity, far away, times the exponent of the optical depth. Tau of z is the optical depth at some altitude. You've probably heard of optical depth before if you're a physics, astronomy, solar atmosphere grad student. Optical depth is the cross-section times the column density. That's the amount of stuff in that column between you and the light source. And then I'm going to throw this mu in. This is the cosine of the solar zenith angle. That takes the angle of the sun into account, right? So you get this equation that says that tau is change of altitude over h. This is density here. So remember density from the last slide? This is your density. And here's your cross section. And so radiation times all of that equals your ionization rate. Right now, we ended up with two exponents because there's an exponent in Beer's law and there's an exponent in the law of atmospheres. So now we have these embedded exponents and we can collect them and have this thing that says the ionization rate at any altitude is I sigma n e to the change of altitude over h minus tau. And so this is the Chapman function.
Are we ignoring source functions? We're just going to look at intensity of sunlight coming in from infinity, but we're not getting the opposite happening.
We are ignoring multiple scattering. Is that what you mean by source function? Yeah. Good question. This is single scattering. This is actually no scattering. This is pure absorption. And it's a great approximation for the ultraviolet, what we're talking about here. For certain emissions within the atmosphere, it's not a good approximation. And as you get, for instance, into the visible, we know that there's multiple scattering because when we look at the sky today, it looks blue, which is evidence of multiple scattering. So we're not bouncing photons all around. This is just keeping it simple, just pouring radiation into the atmosphere and seeing where it lands. And so Sidney Chapman, there's a lot of things named after Chapman, so you got to be careful. He was here. I had his desk when I was a postdoc. It had magical properties. It's wood, for one thing. So this is the Chapman function. And it looks sort of like this. Comes down, essentially following the scale height, exponential drop off. This is the ionization rate, or energy deposition rate, or anything, where the photons landed. And then it reaches some characteristic altitude, and then it drops off rapidly below that. So as the sun sets, this is for overhead sun, solar zenith angle, SEA 0. As the sun sets, you get a longer and longer path length, so the peak is attenuated higher in altitude and drops off, and it still drops off very fast. When you're almost sunset, then the peak is very high and attenuated even more. Up here, these lines are identical, but as you come into the atmosphere, depending on the angle of the sun, you get deeper penetration for an overhead sun. That I think is intuitive. So the deposition of energy by a Chapman function makes a Chapman layer. You can see that this is sort of layered. It's not really layered, but again, log plot, it's pretty layered. Most of what's going on is happening right here in a range of just a few tens of kilometers. Now, how do we find where this layer is? What's the peak? What's the peak of a Chapman function? Well, a little more calculus. If you want to find the peak of something, what do? You differentiate and set equal to 0. So let's do that. Here's the Chapman function. I'm going to differentiate and set it equal to 0. And I will leave as an exercise for the interested the process of actually differentiating this. It's actually not too bad. It's just application of the chain law a couple of times. When I first moved out here, they would say, chain law is in effect on Vail Pass tonight. That's mystified, It's chain law. It's a fundamental theorem of the differential calculus. It's always in effect, everywhere. So then you get this simplification, inverse of the scale height plus tau over the scale height equals 0, or tau equals 1. The peak of a Chapman function is a place where the optical depth is unity. And when you see one of these plots, which you maybe have seen before, describing where in the atmosphere ionization or dissociation, where the energy lands, and it's represented as one line, as if it all landed at one spot, which it doesn't. But if this represents the peak of where it lands, what that is it's the It's the surface, it's the tau equals 1 surface in the atmosphere with respect to solar radiation for an overhead sun. And so this is the linear version of that color plot I showed up. Here in the extreme ultraviolet, you have energy deposition high in the ionosphere, making the ionosphere. Here you have stuff breaking apart O2. Here it's making ozone, and here it's being absorbed by ozone, and then finally here it reaches the surface. Here,
This is without clouds, I assume?
hmm?
This is without clouds.
Yeah, well, there aren't any clouds on this plot because I stopped at 3,000. Yeah, I mean, 420. Clouds are confined to this region here, and of course if you want to do this radiative transfer in the troposphere for say a major climate model, you have to consider very carefully how you do the radiative transfer in and around clouds, how you parameterize the amount of clouds, and how you do the multiple scattering and re-radiation and absorption within the atmosphere. There are, in fact, clouds way up here. Very interesting, noctilucent clouds, but they don't have much of an effect. They're very, very tenuous. So here's a close-up of that same model solar spectrum. Red for the high activity, yellow for the low activity, and one superimposed in there so you can see the variability. And somebody asked about these yesterday. These are these continua, the carbon, hydrogen, and helium continua, and then all of these lines. UV is and especially the soft X-ray and the X-ray are really dominated by individual emission lines, and those can be highly variable. And so when that gets dumped into the ionosphere, this is now a close-up of that of that energy deposition plot. It looks something like this. Now these are each individual Chapman functions. That's why I made this plot. I just plotted the Chapman function at each wavelength, one pixel at a time, to build up a plot. Here's a very important one: the helium-2 emission. Helium-2 meaning He plus. Helium-1 is neutral plus. Somebody asked, "What's iron-15?" It's like that means iron plus 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 plus. They just say 15, meaning 14 pluses, just to confuse you. And this is really the most important ionizer right there, and you can see that. And now at solar maximum, two things happen. The atmosphere swells up, and the radiation becomes more intense. So this plot turns into that plot. Also, these soft X-rays become a lot more important at solar maximum because they're more variable, and they carry more energy. There's not a lot of them, but they're very energetic, and the ionization is ultimately proportional to the energy, roughly. So here's that altitude structure plot again. Just to remind you, solar max, more ionosphere; solar min, less ionosphere; day, F region; night, F region but weaker; E region, and especially the D region, largely disappear at night. So, but remember all that ionization is mostly happening down here between 100 and 200 kilometers. This was my motivating question number 3, I think. So if the ionization is happening down here, why is the ionosphere up there? And why is it still around when the ionization stops? Okay, well, here's the bigger picture showing neutrals and ions on the same plot, 10 orders of magnitude, and now showing all the different pieces, all the constituents, the species of the thermosphere and ionosphere. Atomic oxygen taking over as the dominant species above 200 kilometers, molecular nitrogen dropping off fast but dominant below 200 kilometers. O2 starts as a major player and then fades away to nothing. And then for good measure, I put helium and hydrogen. And because they're so light, they become important. Well, we're no longer in the fluid regime up here, but helium takes over at some point. At some point, helium becomes the dominant species, strangely enough. And then above that, you finally get to the place where or H plus. Protons become the dominant species, way up there somewhere. Neutral hydrogen is never quite, I don't think it ever quite makes it to number one, because by the time you get at high altitude, it's mostly protons. And a little He plus. O plus is orange here. That is the dominant species throughout the F region. Makes sense. Most of the atmosphere is O. It ionizes, makes O plus. Ionized atomic oxygen. Lower down, O plus drops away, and we have mostly NO plus and O2 plus. Molecular ions. That makes sense because we're in a molecular atmosphere. But we don't have much N2 plus. It's mostly NO plus and O2 plus. And the reason for that has to do with the way the ion chemistry works. This is a little complicated diagram, but it's actually vastly oversimplified. This is the main ions and the main chemical reactions. You have ionization pouring into the atmosphere. It hits N2, O2, O, and makes N2 plus, O plus, and O2 plus. That sets into motion a chain of chemistry. The N2 plus falls apart into N and N when it encounters an electron. It's called dissociative recombination. And it also reacts with O and O2. So there's many ways to lose N2 plus. So consequently, we don't have much of it. It's a very important pathway, but it's very low in density. O plus, same story, but we do have a lot of O plus. And then once there's a lot of molecules, N2 and O2, all of this ionization moves down into these species. This is arranged in order of energy of ionization potential. So these reactions run downhill from the higher energy ions to the lower energy ions. And then finally, the only way you can get out of being an ion once you're one of these guys is to do dissociative recombination. Ion recombines with electron, and then the extra energy is carried away by dissociation. Comes together, breaks apart. Dissociative recombination is very fast and exothermic. So the photon flux enters the atmosphere. The ionization processes convert photon energy to chemical energy. Dissociative recombination converts the ionization energy to dissociation energy, fragments of molecules. And of course, when they fly apart, they carry kinetic energy in a sort of a random way, which is what we call heat. So this is why making the ionosphere heats the thermosphere. It's because the residue from that process contains kinetic energy. So you started with photon energy, chemical energy, and well, ultimately kinetic energy, and also the chemical energy of these dissociated products. So the big molecule smashing machine. Doesn't happen directly necessarily, but all these guys who started off as perfectly good neutrals end up as N's and O's, especially O's. And these are some of the types of reactions we've been talking about. This one's very slow. You can just take an atomic ion and recombine with an electron, but it's very slow because you have to have a very specific photon in order for this to go, because there's no other place to put the energy. Dissociative recombination is very fast because you have a molecular ion, recombines an electron, you get the products and some kinetic energy. So you have a very broad potential for this happening because the kinetic energy can be anything. You have a place to put the extra energy of reaction into the kinetic energy of the products, their heat. Very fast. Charge exchanges can also be fast. You take an ion, it meets a neutral, and they do a little do-si-do and switch the electrons around. Then there's atom-ion interchange, which is a lot like that, but when you do atom-ion interchange, you pry something off of the neutral or the ion, break a bond, and now the ionization is on a new species. And that, because this reaction has to break a bond, the rate at which it goes depends on how strong that bond is and a bunch of other quantum stuff. And so these are sort of fun. I probably going to run a little long, but my next talk is a little shorter. So I'll just show these for fun. The Comet program next door put these together just to illustrate. Here's one of those atom-ion interchange. Whoops. Now I'm going to have to find my cursor. If I don't find the cursor, it won't play. That work? There we go. Boom, atom-ion interchange. Try another one. That took an N2 plus and made an NO plus. This happens pretty fast, so that's why we have so much NO plus, not O2 plus. Let's see, here's the dissociative recombination. I have the NO, which we made up here, and it meets an electron. Recombines and breaks apart. Okay, enough of that. So if you have a molecular atmosphere, those fast associative recombination reactions, I'm using M to be any molecule, very simple chemistry. Just imagine we have just an atmosphere made out of M2, okay? So you have an ionization rate and a recombination rate. And you could say, well, this is fast, so it's an equilibrium. So the production equals the loss. The loss is the rate coefficient times the density of the two species. We assume that there's charge neutrality. Sum of the electrons equals the sum of the ions, because if they doesn't, the electrons will move quickly to reestablish charge neutrality. So it's pretty simple. The electron density is the square root of Q over alpha. And in the E region, where you mostly have molecular ions, it's mostly in equilibrium, and the chemistry is very fast, and the dissociative recombination rates are all pretty much the same because they're so fast. This kind of works. And so this formula is approximately right, and that means that the E region is, in fact, a Chapman layer, created by a Chapman layer of ionization, and it's a pretty good-looking layer. It's really a region, but we call it a layer. F region is completely different. Up in the F region, the lifetime of these atomic ions, O+, very long. And so they diffuse. They don't just chemically recombine. And so the F region is not a Chapman layer at all. It's a balance between chemistry and diffusion. And since the lifetime of O+ is so long, that's also why the F2 region, the high altitude F region, sticks around at night. Lifetime of O+ is more than a day, so it lasts overnight. It fades away, but it lasts overnight. So the F region here is not a Chapman layer. It's constantly trying to diffuse downward and upward both, but primarily it's diffusing downward to its demolition in the lower atmosphere, where it runs into lower thermosphere, where it runs into molecules, and then up to the peak, chemistry is in charge. So really, the peak is really the crossover between where diffusion is in charge and chemistry is in charge. And that's all because of this chemistry. Look at the O+. You see, remember I said N2+. It can dissociatively recombine very fast. This is pretty fast. This is a charge exchange, very fast. But O+ gets stuck because this reaction is slow. This reaction is slow because there's not a lot of O2. Remember, the O2 is no longer a major player up at 300 kilometers. So there's not much O2 for it to do this. It could do this, but it's slow because N2 is not very reactive. N2 bond, that triple bond, if you remember your undergrad stoichiometry, it's the strongest bond in nature. Very hard to break this apart. Hard to do this atom-ion interchange reaction. So the O+ gets stuck and has a long lifetime and creates a very interesting F region ionosphere. And because you have a nighttime ionosphere, That means you can get all sorts of electrical circuits going. You get this equatorial electric jet. This is just a high-level schematic of the ionosphere current system. Notice there's a prominent thing that I've left out completely. I mentioned that I was going to leave something out here. What's all this stuff here? Yeah, it's aurora. This is the magnetosphere having something to say about stuff. This is space weather going on. You have currents going in and out, controlled by the magnetosphere, and there you have precipitation going along with that, which makes it aurora ionization, auroral displays, creates a lot more E region, but episodically. Yes?
So on this diagram, one thing that's always confused me is where's the sun pointing?
Ooh, where's the sun? Ooh, where's the sun?
We're trying to get this distinction between daysight and night side,
Yeah, yeah.
and I get a little bit confused.
This is plus, this is minus. I'll try to think this through. The terminator is in here, and the current is flowing. You see, you got to remember the current goes opposite, right? So, but the electrons are going that way. The ions are going that way. So you get this westerly. So the sun's over here. I think that was my recollection. If I've thought it through on the fly correctly, I'm thinking that the sun's coming in like this. You disagree? You think it's coming in over here?
Let me interject before Jan says, this is one of the things that always drives me nuts about, I noticed in the ionosphere group, but it drives me nuts all the time, is you get these wonderful pictures and you go, I have no idea what I'm looking at because I don't even know what direction is up, so.
Well, you know what? This is north. This is south. This is in. This is out. That part's easy. The rotation of the Earth. You caught me there. It's a good question. Art Richmond put this together, and he's right upstairs. We can go ask him. And I just threw this in. I wasn't even going to show this today, but I figured I should say something about the magnetospheric interaction and the electrodynamics. And what the real purpose of this diagram is to show the linkage between the equatorial electrodynamo, the hemispherical connections, and how it maps, how it joins up with the magnetospheric current system. So you have in this very simplified form, a global potential that is described both by this internally generated process, controlled by the atmosphere, and by this externally imposed process, controlled by the magnetosphere.
I think we're looking at the day side here.
Yeah.
Because if you have, the solar wind was coming from behind us, then you'd have a U-cross-B electric field that would be going from right to left across.
There's no solar wind in
It's
here.
not drawn, but that's how. But you can infer it from the sign of the potential in the.
There's no solar wind in the ionosphere, really.
No, but that's what drives.
You're trying to
the
infer
solar
this?
wind driving
Yeah.
the field lines is what
Yeah.
triggers that potential.
Yeah. I think that's right. Like I said, I'm saying that the sun is here, but close enough. Now, if we just look at the equator, we have that current, that equatorial electric jet along the so-called dipole magnetic equator. What that does is, through the E cross B force, it drives the plasma up in altitude, where it then can diffuse back down along the field lines, because the field lines are virtually horizontal here at the equator. And what that does is create these anomaly regions that on an empirical model look like this. These big bands of ionization about 20 degrees on either side of the magnetic equator, which of course it has a very interesting characteristic as you come around the geographic equator. On this, I made this plot, so I know where the terminator is. Terminator is over here. This is essentially the night ionosphere with these big bands of ionization coming, stretching into the into the night and then towards dawn. Here's a somewhat more dramatic version of that. In this case, not neglecting the auroral processes. This is a model, an NCAR model of the thermosphere and ionosphere. Aurora makes a lot of ionization in the E region during storms. That sets up a global enhancement of temperatures, which changes the composition, that atomic oxygen to molecular nitrogen, which is very important. And that has a lot to say through a combination of electric fields and chemistry on the F region electron density. So you animate that. See, here comes a big auroral storm right there. This is just day-night here in the E region. And that big auroral storm has a big effect on the temperature, which is what will happen next. When the storm hits, you get first in the polar region, but then globally, very, very rapidly. Big temperature wave spreads out over the globe. And that changes the scale heights and changes the atomic oxygen molecular nitrogen, which is very important for the ionosphere. Consequently, the ionosphere, which starts out with this equatorial structure, ends up looking completely bizarre in this particular simulation of this particular storm.
Scott, are you getting close to a break?
Yeah, this is my last slide. I just thought, if you wanted to see them all at once, that you could see the dynamism of what the real ionosphere looks like when it's disturbed by magnetospheric storms. I do have one more slide that is peripheral to this talk, but it's apropos to conversations we had yesterday. And also because I think I was supposed to talk about the seasons of the upper atmosphere and the ionosphere. This is that model applied to 18 years of thermosphere variability as inferred from the motions of orbiting objects. All that space debris you saw yesterday. You can use that space debris to infer how dense the atmosphere is by tracking it. And conversely, you would like to be able to know how dense the atmosphere is so that you can do a better job of tracking it. So the black is the measurement of the atmosphere's density at 400 kilometers at using this technique applied by John Emmert at NRL. And the red is our attempt to model that using the model I was just showing you, the TIE-GCM. And the lines are the 81-day smooth of the individual dots, which are the daily means. And you can see, well, we're doing a pretty good job. And you can see that there's all this daily variability. You can see there's this huge seasonal variability. And of course, the enormous solar cycle variability. The seasonal has to do with the composition of the atmosphere as it responds to hemispherically differential processes. And then, of course, you can see these big spikes, which are storms. There's one other thing on this plot, which is you notice that in both the model and the measurement, this solar minimum is about 30% lower than that solar minimum in this particular parameter of density at 400 kilometers. That's kind of a lot. Up until about 2007, we kind of assumed that at solar minimum we got back to a sort of a basic ground state of the atmosphere and the sun, and then we could sort of compare one minimum to the next and intercalibrate. Can't assume that anymore. And the only point I wanted to make about this, because it came up yesterday, is that the F-107 radio flux doesn't account for this. In order to do this, we had to use actual solar measurements. Somebody was saying, well, you should be using actual solar measurements. Well, we are, yes.
So how much of that 30% reduction is due to the instantaneous value of PUC flux versus the fact that the minimum lasted longer and perhaps had more time?
The thermosphere is going to equilibrate in a matter of days. So it's not just that it was a long time. However, the fact that it was long may have something to do with it reaching a lower level of overall activity on the solar side. Additionally, it was very quiet geomagnetically. And it is an active, controversial area of research as to trying to apportion the various effects here. Solar EUV, geomagnetic heating, and then internal terrestrial processes, such as anthropogenic processes. And I could be glad to point you to extensive literature on that subject, it's not, its only real relevance in terms of the discussion today is that this is, I think, places our understanding of the space age variability of the sun in a somewhat larger context. As people have pointed out, that I persist in calling this the anomalous solar minimum. It's only anomalous if you're a space age kind of guy. If you look at a 100-year or a 400-year horizon, it looks like maybe this is something that happens from time to time, and that maybe gives us a window into solar variability on longer time scales. Thanks. I have one other question, I think.
So, these measurements have uncertainties in it when we try to compare this minimum with that. So, what are the uncertainties from that? Is it quite significant?
It's a very significant change, but there's enormous variability in the system, right? Since the solar cycle change is about an order of magnitude, you could say, well, 30% isn't really very much. But in terms of the lifetime of orbiting objects, for instance, I believe the Hubble Space Telescope is catching a break on account of the relatively weak solar cycle 24. The cumulative effect, it can be quite significant. Jan?
So do you want to go back to your diagram with the O plus, the four molecules, atoms in your chemistry? That one. You know, you showed how the aurora kicks in, and you point out that the O plus channel to N2 to the O plus is very small, right?
Yep.
But during the storms and the large energy deposition, that reaction rate is very temperature sensitive. And one way of changing the electron density profile in the ionosphere, especially at high latitudes, is for the O plus to influence that interaction rate, because we do all that heat in the upper atmosphere, and all of a sudden O plus becomes NO plus, and that then
Which then goes away. Yeah, it's a mechanism for the aurora to sort of destroy itself. I didn't point it out, but on this diagram I say H nu, photons, and E star. E star is code for energetic electron. So all of these processes, which here I was mostly talking about photons, are equally applicable to auroral electrons. When I do the aurora talk, which I don't have time to do, I use the same plot, except I point to the E stars instead of the H nus. The aurora, you make ionization from the E stars, and then the same stuff happens. But it tends to be lower down. So this stuff can go. And so the aurora tends to have more of the molecular ions. And as Jan's pointing out, some of these reactions can pick up the pace a little. And so you get more molecular reactions. There's another way. These E stars can also be photoelectrons. Those are the electrons that are made from ionization itself. When you ionize N2, make N2 plus an electron. That electron has extra energy. We call it a photoelectron. And then it can make more ionization, maybe. Or it might be a secondary electron. When a high energy auroral electron comes smashing into the atmosphere, it ionizes N2, makes N2 plus another electron, which has extra energy. So it can then make another electron, another ionization. And then, so you have this cascade process, constantly making more and more and more and more. And that's why I said that really the ionization rates in both the auroral and the photon cases are really proportional to the energy coming in. Because all that energy has to go somewhere.